Hey everybody. I want to do one more example of finding a Taylor series. So in this case, we're finding the Taylor series for f of x equals 4 natural log of 7 minus x. And we're going to find it at x equals 0. So sometimes people call that a Maclaurin series. But it's still just a Taylor series. It's just the ones located at 0, right? Built around 0. And then we're going to find r, the radius of convergence. Okay. So let's go through the process again. When we have a Taylor series for a function, right, what we're trying to do is write it out in this form, all right? Or more explicitly, right, it's an infinite polynomial. Do one more term here. Okay, so there's a nice compact summation notation. There is the more explicit formula. And to be clear, sometimes we can't really write it in the nice summation notation if the definition of those coefficients doesn't follow a nice pattern. And actually, in this case, we'll see, I believe in this case, we see that the first term can't really fit into that summation notation because it follows a different pattern than the rest. But you'll see what we do. It's not a big deal. In either case, you're still writing out a series like I have here. Notice everything here, so everything is well defined, is easy in the sense that we know what it is when we start, except for these coefficients, right? Which I know is like the big part of the problem. But I just want to make sure we get the easy parts. So for instance, in this case, since we're doing it at x equals 0, that just means the place we're locating it. And in this formula, that's my a value, okay? So in other words, I already know this is going to look like just putting in 0 for a, and I'm going to get a series that looks like this. Okay. Now, still, what that leaves us with is how do we find the coefficients? But the coefficients, we have a very simple formula. The nth coefficient is just the value of the nth derivative of our function at a, in this case 0. So for us, it's going to look like this. Okay, that's what each of these are. Meaning we find those derivatives, we evaluate them at 0, we divide by n factorial, we divide the 0th derivative by 0 factorial. The 0th derivative is just the function. The first derivative at 0, we divide by 1 factorial, the second derivative at 2 factorial, and so on and so on. So what that means is we want to compute derivatives. So I will start with the function, what we're calling the 0th derivative. F prime, we have 4 times 1 over this. I'm going to write it as 7 minus x to the negative 1. I'm doing this because I'm going to be taking several derivatives here. And it's easier for me when I can just see the exponent because we're going to use the power rule. I don't want to use a quotient rule or anything like that. So if I write it 1 over this, I either have to like do a little bit of extra work in my head to track those exponents, or use a quotient rule, which is always best, if possible, to be avoided, in my opinion. But I'm not done with this derivative. We have a negative here. So the chain rule says we divide by or multiply by the derivative of the inside, which is negative 1. So we get a negative out front. Then our second derivative. So what's going to happen? We're going to get negative 1 coming down times negative 4 gives me 4. And then we'll have 7 minus x to the negative 2. But then we get another chain rule. We multiply the negative again. And so we get our negative back. F triple prime. Same thing. I'm going to get negative 2 times negative 4. Now I'm just going to write 4 times 2. I'll say why I'm doing it this way in 1 second. And I'm leaving them positive because we've got a negative times a negative. So negative 4 times negative 2 will give us a positive 8. I'm writing it as 4 times 2 for convenience. 7 minus x to the negative 3, but then the chain rule from the inside gives us a negative. Let's do one more, and then I believe we'll be able to see what's happening here. So I've got my 4 times 2, negative, and I've got a negative out here. I'm going to get a negative 3. So those two negatives are going to cancel. 7 minus x to the negative 4th power, and then I get my negative from the inside. All right. So I want to notice something. That negative 4 is always sitting out front. I'm going to kind of segregate these coefficients right here. And I'm going to do one more. And you might already see the pattern, but I want to make it perfectly clear. I'm looking at the 5th derivative. So again, now I'm going to be bringing down a negative 4. I'm just going to put it in these parentheses with these things. We got a negative here, so we have a positive. And then 2 times 3 times 4, 7 minus x to the negative 5th, then the negative coming from the chain rule, okay? So now I think the pattern is pretty apparent. Notice what's happening. We've always got this negative 4 out front. That's just sitting there, right? We always have this 7 minus x, and at each step, we get a larger negative number, or smaller. I think of them as larger, but in the negative direction. In either way, right? We're going negative 1, negative 2, negative 3, negative 4, negative 5. Notice that the power here is always the number of the derivative. At the first derivative, it's negative 1. At the second derivative, it's negative 2. The third derivative, it's negative 3. The negative 4 is always there. The 7 minus x is always there. What's happening out front? I didn't write a 1 here because 4 times 1 isn't really useful, but we could have written it. So we have negative 4 times 1, negative 4 times 2 times 1, negative 4 times 3 times 2 times 1, or 2 times 3, or here is 1 times 2 times 3 times 4. We're getting a factorial sitting here. Notice this factorial, let's highlight this, is 1 less than the derivative we're on. This is 4 factorial, right? I didn't write the 1, but we could, so this is 4 times 3 times 2 times 1. Here we have 3 factorial at the 4th derivative. Here we have 2 factorial at the 3rd derivative, and so on. Okay, if we did another derivative, that 5 would come down. We'd have a 5 factorial at the 6th derivative. So let's use everything I just said to write down the pattern. At the nth derivative, that negative 4 is always going to be sitting there. We have a factorial that's 1 less than whatever derivative we're on. Right? At the 5th derivative, it's 4 factorial. So at the nth, it's the n minus 1 factorial. And then we have 7 minus x to the negative n. At the 5th derivative, it was negative 5. At the 4th derivative, it was negative 4. So those parts match. So the reason I'm doing this is part of the problem we're doing here is to find the radius of convergence, right? Which means we'll have to use those convergence tests. And to use those convergence tests, we need something that tells us what the nth term looks like. So I need this little pattern. Okay, but we're not there yet. Oh, and this also explains why I wasn't multiplying these out. This is a lot easier to see. If I had 2 and then 6 and then 24, I might not recognize that. Oh, and especially if I multiplied by the negative 4, I'd have negative 8, negative 48, negative 96, right? I'm not going to recognize that there's a little factorial sitting in there, right? And so when I'm taking these derivatives, I tend not to combine things too much because I want to be able to see what's happening. I don't care about evaluating these particular numbers. I care about getting this pattern, okay? So now we're going to evaluate all of these at 0, right? And this part's pretty easy. When we put in 0, these all just become 7 to a power. Notice one other thing. This first one doesn't fit with the pattern, right? That one was our natural log. But after that, this pattern is going to persist. You can see what's happening. We keep pulling out those negative exponents and then getting a negative from the chain rule. So we always end up with this negative. So after that first term, they all follow this pattern. So the first one follows its own pattern. That will keep it outside of, but after that, so I should say something like for n greater than 0. right? That's what our terms look like. For n equals 0, the 0th derivative, it's got its own thing. So let's evaluate these. Remember our formula right here, we're evaluating at x equals 0. So I want f of 0. This is 4 natural log of 7. Then we get f prime of 0 is negative 4 times 7 to the negative 1. F double prime of 0 is negative 4 times 7 to the negative 2. Let's do 2 more. F triple prime of 0 is negative 4 times negative 4 times 2 times 7 to the negative 3. I'll just fix it here. The fourth one we already saw, plugging in 0, we get negative 4 times 3 times 2 times 7 to the negative 4th, and on and on. And so the nth derivative at 0 will be negative 4 times n minus 1 factorial times 7 to the negative n. Okay? So now let's take just this piece we have here, right? Really, once I have this pattern, I can plug in the 0. We do have to be careful about this first one because it doesn't fit with the rest of them. So we need to be conscious of the fact that this one follows a different pattern. So let's look at our coefficients now. The nth coefficient, remember, I'm just looking back at this formula, c sub n is equal to the nth derivative at 0 over n factorial. We just came up with a nice formula for the nth derivative at 0 right here, so we can put that in right here. So when we do that, we get the nth derivative is equal to negative 4 times n minus 1 factorial times 7 to the negative n, and all of this gets divided by n factorial. So c sub n, we can do some simplifying. N minus 1 factorial over n factorial is negative 4. Sorry, negative 4 is negative 4. N minus 1 over n factorial is 1 over n, so we can write it like this. Maybe this is nicer written as, I don't know what the nicest way to write it is. Maybe something like n times 7 to the n. If we want to put it in the denominator. It's arguable what's the easiest way to write this. This is now a formula that spits out all of our coefficients except for the 0th coefficient. That one is just this. Right? It doesn't follow the actual pattern. In other words, what I could write down is that f of x is equal to, so I'm going to do the summation, but I can't start my summation at 0 because the 0th term doesn't follow this pattern. I'm putting in my coefficient, negative 4 over n times 7 to the n, x to the n. But I have to put in that 0th term outside because it doesn't fit the pattern. Okay, so again, all I'm really doing here is looking at this formula here, except this term, the C naught term, doesn't fit in it, so we write it outside and start our indexing at 1. Okay. Now, this gives us the form of our equation. So we could take this and write out a few of the terms. So we have 4 times natural log of 7 plus, when n equals 1, let's see what we get. We have negative 4/7 times x. I'm just putting in n equals 1. Then for n equals 2, I get negative 4 over 2 times 7 squared, or 49 x squared. Of course, you can simplify some of this. I'm gonna leave it as is for now. It's not important to what I'm trying to accomplish. Let's do one more. We'll get negative 3 times 7 cubed, x cubed, and on and on and on. right? So there's our Taylor series, right? These are our coefficients. This is C naught. This is C1. This is C2. This is C3, right? And then the x squared, x cubed, those are really x minus 0 in the formula. X minus 0 squared, x minus 0 cubed, but of course we don't write the 0 out. So there's our terms, okay? And so this is nice. This is a good example where we couldn't quite get everything into the summation, but if we're careful with how we do our work, we might notice a pattern. Now, here's where that pattern becomes very useful. We want to find the radius of convergence, okay? We want to see where this thing converges. And to do that, I think in this case, the ratio test is going to be the easiest. So I have to look at the n plus 1th term divided by the nth term, and the absolute value of those, and multiply or take the limit as n goes to infinity. So without a nice formula for the nth term, this is very difficult to do. So let's use this. The nth plus 1 term is going to look like -4 over n plus 1 times 7 to the n plus 1 times x to the n plus 1. The nth term is going to be -4 over n times 7 to the n x to the n. Okay? When we take the quotient of these, so what's going to happen? Well, when we divide something with a -4 in the numerator and the denominator, those -4s are going to go away right away. That's easy to see. And what'll be left, we'll have x to the n plus 1 over 7 to the n, oops, I skipped one piece, over n plus 1 times 7 to the n plus 1. And then we'll be multiplying by the reciprocal of the other one without that -4. Those we're going to cancel. I just wanted to get at least one thing out of the way. Now looking at this, we can do some more simplification. X to the n plus 1 over x to the n gives me an x. 7 to the n over 7 to the n plus 1 gives me a 7. And then we've got n over n plus 1. Okay, that is our quotient of terms. So now we want to take the limit as n goes to infinity of the absolute value of x over 7 times n over n plus 1. We can pull out that x over 7. Oops, this is supposed to be a limit, not a natural log. The x over 7 is like a constant as far as this limit's concerned. As n changes, x doesn't. So n over n plus 1, as n goes to infinity, that becomes 1. It gets closer and closer to 1, I should say. And we get simply x over 7. So remember, this test tells us that the series converges if this limit is less than 1. So we want to know where is the absolute value of x over 7 less than 1. This is equivalent to saying x over 7 is between -1 and 1, or x is between -7 and 7. And so here it's easy to see that the radius of convergence is equal to 7. Okay, so that's our process. One other comment about that. This doesn't tell us what happens on the endpoints. I'm going to skip that part right now. But I'll tell you, this does not converge at 7. If you plug 7 in for x, you end up with -4 over n as your series, the terms of your series, which does not converge. It's a p series is one way you could think about it. You can factor the -4 out. That's one test that would work there. It does converge at -7 by the alternating series test. So I'll let you guys work on the details of that. We should have already guessed it wouldn't converge at 7 because this function is not defined at 7. If you put in 7 in the original function, it's undefined. Natural log of 0 is not defined. All right, so it's a lot of work, but it again is just following this formula. All we're trying to do is figure out the coefficients. To figure out the coefficients, you're taking derivatives, evaluating at whatever value of x you want to center your series at, right? In this case, it was 0, but it can be anything. You evaluate all these derivatives and you divide them by n factorial for each corresponding derivative. Of course, part of the trick is finding the pattern, right? And so that just takes practice. And I really advise, is one of the few times I don't like to combine and do the simple multiplications, because here I'm really not caring about the actual numbers as much as coming up with this formula that we came up with. All right, let's do one last thing. Let's take a look at a graph of this. So here is our function for natural log of 7 minus x. And you can see I've programmed in the series already. Now I can't program in an infinite series, so I've got the first 100 terms. This might take a minute for the computer to compute, and there we see this graph. And notice here are lines at x equals 7 and x equals negative 7 and 7, right? Notice what the orange graph is the function, or is the series. Notice it follows, it looks like it's going to continue following the asymptote that the function has at 7, but it passes through the asymptote here because it's going to hit the value of the function there. It does converge there, and it will hit the value of the function at that point, and then it will skew away from the function, bend away from the function, and do its own thing. And so we see in this picture that it appears to do, right, again, it's only 100 terms, which is not that many when we're talking about infinite series, but you can see that it's already appearing to be pinned pretty close into this negative 7 and 7, right? In the infinite, it just simply diverges past this point, and here it diverges. We get higher and higher, or lower and lower values as we get closer to that asymptote. Okay, that is it for this one. Thanks, everybody. I will see you next time.